I'm going to start with a review of set theory. To skip this, look in the video description for a link to the problem solution. I find it helpful when dealing with sets to have a Venn diagram up for reference. Let's put some elements into this set. The set A contains the elements 1, 4, 5, 9, and 11. The set B contains the elements 2, 4, 5, 8, and 10. The union of A and B consists of all of these numbers, and the intersection consists of the elements that are in both sets A and in set B. This backslash between the A and B means that we are looking at the elements that are in set A but are not in set B. So that consists of the elements 1, 9, and 11. These are in set A but are not also in set B. The elements that are in set B but not in set A are 2, 8, and 10. Finally, we'll use this notation to indicate the number of elements in set A. In the AOPS textbooks, they use this notation. The number of elements in set A is 1, 2, 3, 4, 5. The number of elements in the intersection of A and B is 2, 4, and 5. For more information, check out the AOPS Intermediate Counting and Probability book. In particular, look at Chapter 2 for more information on set theory. Now let's go to the problem. Using our Venn diagram for reference, let's let omega be the set of numbers 1 through 5. Let's let X be the set that is the intersection of A and B. Let's let Y be the set of elements that are inside A but are not in the intersection of A and B. We'll let Z be the elements that are in B but not in this intersection. And we'll let W be everything that's outside of either A and B. We note that all 5 of these sets combine to form omega, and all of these sets are disjoint, meaning they have no elements in common, which will make it easy to add up the elements. Here is the given equation. Let's substitute for our variables. The number of elements in A is the number of elements in X and Y. The number of elements in B is the number of elements in X plus the number of elements in Z. The number of elements in this intersection of A and B is the number of elements in X, and then the number of elements in the union of A and B is the number of elements in X, Y, and Z. These are all just numbers, so we can multiply them out. Foiling the left-hand side and then the right-hand side, we find common terms on both sides of the equation. So we're left with the product of the number of elements in Y and Z is equal to 0, which means either Y is empty or Z is empty. So we're going to count the number of ways that Y can be empty and the number of ways that Z can be empty. In doing so, we're going to count twice the number of ways that both Y is empty and Z is empty. So we're going to subtract this once to avoid double counting. Let's count the number of ways that the set Y is empty. That means that the elements in our remaining sets, X, Z, and W, is going to add up to 5. The elements in these sets are distinguishable. For example, the element number 1 can be in either set X, set Y, or set W. That's 3 ways. Likewise, number 2 can be in either of these 3 sets. So that's another 3 ways independently of set 1. This is the same for all the numbers from 1 to 5. Since these events are all independent, we can multiply them. And we get 3 to the 5th ways that our elements 1 through 5 can be distributed into these 3 sets. Z can also be empty, and there's really no difference between Y and Z, so the number of ways of distributing our 5 elements among the sets X, Y, and W is also 3 to the 5th. But we're double counting the number of ways that both Y and Z can be empty. That leaves our 5 numbers to be distributed between sets X and W. Number 1 can be in either set X or W, so that's 2 ways, and so on for all 5 numbers. That's 2 to the 5th ways. So our final calculation is to count the number of ways that set Y can be empty, the number of ways that set Z can be empty, and then we subtract the number of ways that both Y and Z are empty. So our answer is 454.